This is Analysis of Time Series, Chapter 5, Parameter Estimation and Model Identification for ARMA Models. So in part 1, we're going to be reviewing likelihood-based inference. We're going to be setting up the context for ARMA models, but really the things we're going to review: maximum likelihood estimation, Fisher information, profile likelihood, bootstrap standard errors. These are all more general than time series analysis. They just happen to be useful for ARMA models. So for any data set, y1 through n star, and any probability model, f of y1 through n, we define the likelihood function to be the joint density evaluated at the data, thought of as a function of theta. And very often we work with the logarithm of the likelihood, which here we're going to use script capital L for the likelihood, script lowercase l for the log likelihood. Now, the likelihood and the log likelihood as a statistical tool is a very general technique, and it's been very widely used since it was developed by Fisher in the 1920s. And when you have access to the likelihood function, you have all the standard tools of likelihood-based inference available for you. And time series analysis involves various situations where you can, with sufficient care, compute the likelihood function, and then you're in the business of doing likelihood-based inference. Computation of the likelihood function for ARMA models is not entirely straightforward, which is one of the reasons why historically it hasn't always been carried out. But computation-efficient algorithms do exist using a state space model representation of ARMA models. We're going to see that later in the course, but for now, we can just think of the software as existing to evaluate and maximize the likelihood function for a Gaussian ARMA model. So we don't have to think about the details. We have to think what to do with the capability that we have to do that. Now, when you look in many time series textbooks, they'll tell you about things called the Yule-Walker equations for doing a method of moments. That means matching the mean and variance, and covariance is the autocorrelation function, finding a model that matches those things for the data. This is nowadays mostly of historical interest, because if you can calculate the likelihood function, you probably should. But if you want to read about that, it's in the Shumway and Stouffer section 3.5. It's not entirely irrelevant nowadays for massively long time series and big ARMA models. Sometimes the likelihood function calculations just get too big, and you may have to resort to inefficient, statistically inefficient, but computationally more efficient methods. Here we're going to focus on the common situation where we can, with due care, work with the likelihood. And when we say likelihood-based inference, we don't just mean a point estimate, the maximum likelihood estimate, a famous statistical estimator. We also mean standard errors, hypothesis tests, diagnosing model misspecification, all the things you might want to do in a careful and complete data analysis. So although we're going to focus on likelihood-based inference, and we're going to go through a little bit of the theory, we're not especially concerned with the underlying theory of likelihood-based inference. On any particular situation of interest, we can check the properties of a statistical procedure by simulation, and so we're not necessarily a slave to being able to analyze things theoretically. Here's the maximum likelihood estimator, the famous MLE, which in our notation is theta hat of y1 through n is the value of theta maximizing the density, joint density viewed as a function of theta. Now, you can do this for any y1 through n. We're going to be particularly interested in evaluating the maximum likelihood estimator at the data. We're also going to be interested for looking at statistical properties. what happens when you evaluate the maximum likelihood estimator at a draw from the probability model. There's a little detail about uniqueness of the MLE. If you want to be careful, you can say an MLE, because any value of theta giving the same maximizing value is an MLE, and then if there are many such values, the MLE exists but is not unique. Okay, and so there you go, there's the MLE. Just as a little exercise, you can think, why is argmax of the likelihood and argmax of the log likelihood the same? What property of the logarithm is it that makes these two things the same? Well, well, here we are. So log has many nice values. It's convex, for example. For this, all you need is that log x is order preserving. Which is just really another way of saying it's strictly increasing. Now, we sometimes write theta hat MLE to denote the MLE. Very often we're considering the MLE, and so we sometimes drop the MLE subscript, and depending on the context, it's quite likely that just theta hat is going to correspond to the MLE in this course. So as statisticians, it would certainly be irresponsible to present an estimate without a measure of uncertainty, and the standard way of doing this is to produce a standard error for the estimate. And you can also obtain a confidence interval, often an approximate confidence interval, because often there's some sort of, often it's not a perfect confidence interval. A perfect 95% confidence interval would cover the true parameter value exactly 95% of the time. If your estimate is based on some sort of approximation, such as large sample, for example, then technically you have an approximate confidence interval. And saying approximate reminds you that there's some checking to do to assess how accurate the approximation is in your particular situation. Here are 3 ways to quantify statistical uncertainty in an MLE. One is Fisher information, which you may well have seen in a theoretical statistics course. It's a computationally quick approach. It only works well when the distribution of the MLE is well approximated by a normal distribution. We're going to talk a bunch and use a bunch, something called profile likelihood estimation, which you may not have seen before. In that case, you're learning a really useful new applied statistics technique. It's a bit more computational effort than Fisher information. It's generally preferable in practice. And the last thing we're going to talk about some amount, and sometimes do, is a simulation study, which is essentially a synonym for a bootstrap. Here's the observed Fisher information, a textbook way to get standard errors. So we're going to suppose that theta is a d-dimensional vector. And so then we can write theta equals theta 1 to d, where theta little d is the dth component of theta. Then the Hessian matrix of a function is the matrix of its second partial derivatives. And here we go, we have the second derivative of log likelihood, evaluated ij, is this thing, and then the observed Fisher information is the matrix of all these things. And then a standard asymptotic approximation to the distribution of the MLE is that theta hat of y1 through n, that's when you apply the maximum likelihood estimator to a draw from the probability model, the estimate should be roughly unbiased and have variance roughly I inverse. And this is where theta is the true value. So the MLE is approximately unbiased with variance asymptotically attaining the Cramér-Rao lower bound, if you know what that is. There's this property that an unbiased estimator essentially can't have lower variance than the Cramér-Rao lower bound. That's why it's called the Cramér-Rao lower bound. And estimators that have this property are called asymptotically efficient. We say it's asymptotically efficient. And on the previous slide, I wrote this approximately equal sign, which whenever you see approximately equal, you start thinking, well, what does that mean? And so I'll say something about that. It could mean two similar but slightly different things. One is that one could write a limit statement formally justifying this approximation in a suitable limit. So for instance, a central limit theorem says that if say a properly normalized average is large enough and things are independent, then it will head towards the normal distribution. So for a finite sample, you could say it's approximately the normal distribution. Almost equivalent, approximately equal can mean this approximation is useful in the finite sample situation at hand. A difference there is that you're not quite promising that the finite sample situation at hand even has a sort of natural limit. Okay, so once you have an asymptotic limit of that type, it suggests a confidence interval where you take the standard error corresponding to the standard deviation of that normal limit, and then if you want a 95% confidence interval, you have plus or minus 1.96 times that standard error. And that's what the R function ARMA does when you just ask ARMA to go ahead and do maximum likelihood estimation. Now, when you do time series analysis, you usually only have one time series for some fixed n, so you can't in practice take n to infinity. And if you have a stationary model, at least it's fairly clear what it would mean to take n to infinity, because you would just keep on with the stationary model. If the model's non-stationary, it may not be clear what it would mean to take n to infinity, but it can still be useful to think about asymptotic results because they still suggest approximations, and they suggest normal approximations that may be suitable in a finite sample case. And you can always check how the MLE behaves on your model and data by a simulation study. Okay, so profile likelihood. So let's imagine that we want a confidence interval for one specific component of the parameter vector. Here's this thing called the profile log likelihood. It's we write it as L profile, and it's D because it's for the dth component, and then it's a function of theta D, and it's defined to be maximizing out all the other parameters. So, well, in maximizing the log likelihood over all other parameters. And a couple of properties you can check for that. The maximum of the profile likelihood should be the maximum of the likelihood, because if you maximize out all the other parameters as a function of this parameter, then you maximize over this parameter, you get the global maximum. Now, another really nice property is that if you take the set of parameter values that have a profile log likelihood within 1.92 of the maximum, then that gives an approximate 95% confidence interval known as a profile likelihood confidence interval. So let's just see what that looks like in practice. So you have some parameter theta d, and you have on this axis, I've plotted the profile likelihood, and then this maximizing point here is theta d hat, and what this says is that if I take this distance here to be 1.92, then this interval here is a approximate 95% confidence interval. Okay. You can wonder where the 1.96 cutoff comes from, and the first time you see it, you might think, surely that's a typo. Doesn't he mean 1.96? But it turns out it's 1.92, which is 1.96 squared divided by 2. We'll see why a little bit later. And that's called Wilks's theorem. Something that's interesting to think about, Wilks's theorem, it's an asymptotic theorem. You can probably guess it must be some sort of asymptotic limit. Well, the asymptotic justification of Wilks' theorem is the same limit that justifies the Fisher information for standard errors. So it's not obvious why one should be better than the other. In some ways, they're almost the same thing. But it turns out that profile likelihood confidence intervals tend to work better than Fisher information confidence intervals when the log likelihood function is not close to quadratic near its maximum. This is more common when n is not large, and it's more common when the likelihood surface has some weird behavior. And it turns out that the likelihood surface for ARMA models can have some weird behavior, which is one reason why profile likelihood is useful in the context of time series models. Okay, so the last part of this part, we're going to talk a little bit about simulation studies, which I'll use pretty much interchangeably with bootstrap. If done carefully and well, this can be the best approach. It's just time consuming. So one way to think about these things is that a confidence interval is a claim about reproducibility. And so as far as your model is correct, if you have a 95% confidence interval, that means that 95% of realizations from the model will generate an interval that covers the true value of the parameter. And a simulation study can check this claim directly, right? You just simulate from the asserted model, evaluate the confidence interval on a large number of realizations from the model, and see what fraction cover the truth. In the simulation study, you know the truth. The simulation study does take time to develop and debug, time to explain, time for the reader to understand and check what you've done. And I think that's one reason why simulation studies are not quite as large a solution to everything as they might seem, but it really is worth carrying out simulation studies to check main conclusions and investigate any particularly weird thing you find. Let's just go through how a simulation study constructs standard errors and confidence intervals. This is really no different in time series than anything else, but let's do it in our current notation. So we have some estimator theta hat, And we want to know the statistical behavior of this estimator in a neighborhood of the MLE. And in particular, let's imagine that we want a standard error or a confidence interval for some component, say the first component of the vector theta. Well, we can use simulation to assess the behavior of the maximum likelihood estimator and the coverage of an associated confidence estimator. And we can do that regardless of the details of how this estimator is constructed. It could be a profile estimator, it could be a Fisher information estimator, it could be a method of moments estimator. It doesn't matter, we just calculate it on all these simulations. So these are our three main goals, A, B, C. Evaluate the coverage of a proposed confidence interval estimator, construct a standard error, and possibly modify the confidence interval to give it the proper local coverage. So in A, if your estimator has bad coverage, if it's nominally 95%, but in practice it only has 80% coverage, then you might wonder how you can adjust it to get the local coverage right. And here's the kind of structure of a simulation study. You're going to start by generating, say, J independent Monte Carlo simulations, and I'll superscript them by little j, and they're going to run through all 1 to n data points. And you're probably going to run these simulations at your preliminary estimator, so theta hat, your MLE. And then for each simulation, you can re-estimate a maximum likelihood estimator, and that's going to be theta hat j. It's not going to be exactly the MLE, because in this simulation study, the MLE plays the role of the unknown truth, but we can re-estimate it for the theta hat j's. And then the spread of these theta hat j's tells us about the spread of the confidence interval, well, the spread of the estimator, and therefore the width of the confidence interval we need to allow for that error. And so we generate this interval somehow or other by profile or by Fisher information, for example, and we get some interval theta 1 low to theta 1 high, and it probably has some nominal coverage by design, but we can test the coverage of that by just looking at the proportion of the simulated intervals that include the parameter that's known in the simulation study. And in a similar way, you can take the standard deviation of these re-estimated parameters as a natural standard error representing the chance variability in the parameter estimate in a neighborhood of the MLE. Okay, that's the end of part 1. Thank you.